Good morning, good afternoon, everybody. Thank you for joining the webinar. Today we will have a webinar on deriving water quality indicators and indices using Sentinel-2, but also cloud computing facilities of the European Space Agency. I'm Shuaib Salama. I'm Associate Professor at the University of Twente, Faculty of Geoinformation Science and Earth Observation. So I will start this webinar. So what we will see to approaches of deriving water quality indicators from satellite images and describe a pollution event with a time series of satellite-derived indices. One thing before I go ahead, after this introductory slide, we are recording this session. So if you have an objective on recording, please raise your hand. And I will wait for a few seconds. If I do not see any raised hand, I will continue. Okay, thank you. I think everybody agrees to record this session, so I will go ahead. So basically, satellite measurement related to water quality. You need a water body in the field of view of the satellite, and you observe different signals. So if you look at these colors of those signals at this graph, you would see that the sunlight, which is here in red, comes from top of atmosphere, and then it goes through the atmosphere, reflected at the surface. You have the surface signal reflected as the surface of the water. Part of it will be penetrating the water. If you have a shallow and clear water, this radiation could reach the bottom, and this part will be reflected at the bottom and go up. Part of this radiation will never be able to make it to the bottom, either because the water is, or the water body is deep water, or we have a lot of turbidity. We will look at this later. Part will go to the sensor. So the sun will give the radiation will go through the atmosphere, and then it will interact with the atmospheric constituents, but then it hit the water surface, it penetrate the water, and then interact with the water constituents and go up. If you have a small water target, like the one here depicted, you will have a problem with, we call it edge effect. And this is the idea that the land has a higher signal in the optical part of the spectrum than water. So this signal could interfere in the field of view of the sensor. So basically, and on average, if you look at this visible part of the spectrum, you will see about 20% of the signal will be from this green. We call it watercolor here. But the rest could be coming from the bottom, surface, or adjacent. And the biggest one, so the largest portion or contribution, is basically coming from the atmosphere. So the whole concept here is how light is interacting with the water, and this is what we call them optically significant component inside the water. These are components that actually affect the light, the visible light. So if you go to this website, for instance, you could see a lot of different species of phytoplankton. So what is in the water? If you look at it, you have the water molecule themselves, but you have algae, or we call phytoplankton, and you have a suspended material and dissolved material. So this is part of this phytoplankton, and this is part of the species. We have many species. I just listed 4 just to show you how they look like. But when you go to suspended particle, you have also 2 forms, organic particles and flock together, sometimes with inorganic particle, but then you have this B, what we call them inorganic particles. So if you look at it on a scale like this figure here, shown, you would see that on a lab, if you go to lab, you collect water sample and you put it through a filter 0.45 micron, and everything goes through the filter. It is called dissolved organic matter, and it is in this graph on the left side of the figure, and everything is retained on the filter as suspended materials. And if you look at suspended material, then there are many types, so organic, inorganic types, and they come from different origin. And if you look also at the left side of this graph, you would see the inorganic materials, and also they are formed from many types. All this ensemble of suspended and dissolved material, they give something we call it watercolor. And this is being done actually by one of my student in Brazil, between Brazil and Colombia, there in the sea. What you could see is, because of this interaction of light with those optically active components, we call them scattering and absorption. And this gives a color, a specific color for the water surface. For example, if you have a murky white gray color, this is mostly related to suspended particles. If you have a yellow brownish water like this one here at the lower right corner of this graph, it is mostly dissolved organic matter. And if you have green at the lower left of the graph, this is mostly related to chlorophyll. So this kind of processes how light gets into the water and interact with those suspended and dissolved organic matter is actually the main concept and a main processing concept that we use to detect water constituents from the satellites. But we do not do that just top of the surface. Most of the satellite sensors are at the top of the atmosphere. So they are at height about 700 kilometers above the Earth's surface. So you see the whole atmosphere before you get to the water target. And I show you here two figures. They are the same figure, and they are taken from an airplane flying at 800 meters only. It was a hazy day over water target. And you could see on the left part of the figure, you could see kind of haziness. And this haziness is caused by what we call it the atmospheric effect, because the light, when it gets through the atmosphere, it also interact with the atmosphere, scattering and absorption, hit the water, penetrate through the water, interact with suspended and dissolved organic material, and then it goes up back to the sensor. In this two-way strip, there is a lot of distortion, and the biggest one, as we mentioned in the beginning or in the first slide, is coming from the atmosphere. And we did here a small exercise to try to remove the atmospheric effect. So if you look at the right panel of this graph, you could see these front, which are this front here and the other ones, they are characteristic of suspended sediment fronts. And if you look at the lower panel, you could see that the signal recorded at the satellite, and this is only 800 meters above the water surface, is this the red graph. And after you remove the atmospheric effect, you get the blue graph, and you could see it's about 100%. So 4% at the blue is being recorded with the atmospheric effect as double. So the atmospheric effect could double the signal coming from the water. And it has a very complex effect on the water signal because it overestimates the turbidity in clear water, but also it underestimated in turbid water. And if you have a small water target, it contributes to decrease in spatial resolution. So application related to a satellite for water quality and water pollution detection should have and should actually undergo a very good atmospheric correction procedure. Otherwise, the results could be interpreted in a very undesired way. And this is really one of the most important aspects for data quality before we further and look at the water quality indices and an indicator. You have, when you go back and then apply these knowledge, you have to take care that these data are atmospherically corrected, and you have to take notion that atmospheric correction is the main contributor to the uncertainty in the products. So after we have done atmospheric correction, we have the data themselves, and the data, there is always a confusion between indicator and indices. Indicator normally are those variables of parameters that are used to describe the water quality condition. For instance, an indicator could be how much suspended sediment, the concentration of suspended sediment, or the concentration of chlorophyll A. But in water quality, deriving suspended sediment or a chlorophyll A, if it is, we will come to that later, if it is not on an analytical, if it is not on an empirical approach, it is a more sophisticated term. And here comes the indices. Normally, we take a few indicators and we compute an index. In the same approach, in the same sense, each band is of the sensor that is being registered by the sensor. It could be used as an indicator for how much turbid or clear the water is. And if you combine different bands, you come up with something we call it spectral indices. The term itself could be really confusing, but some indicators are also indices. And this is we find often when we use spectral indices. So you bring two bands of the sensor or three bands and you make an index, and it's an indicator of turbidity. But the normal notion is when you go from data to indicator to indices, you are actually compressing the data. So the data concentration are increasing. You will see that, we will see that in the common slide. So we have data, indicator, and indices, but watch out, indices are sometimes also indicators. When we want to look at an indicator and index, I will give you an example. For instance, I have a turbidity indicator from a satellite, but I would like to have an index that describe the water clarity. So I can use turbidity as an indicator and then convert it to an index. But I could also use kind of spectral indices, but we will do that today. These spectral indices, they are unitless most of the time, but they need another step to convert them to something that is physically recognized, like concentration, suspended sediment, or concentration of algae and chlorophyll. Here is the thing, there is no single indicator or index that can account for and be applied to all types of pollution. Also, indicators are actually mingled with indices indices. But if you would like to be really precise, then you have a data, you can take the data and convert them to indicators. You can have set of indicators to create an index if you want it to be precise. But most of the time they are switched. In this case, we will be a little bit more careful. So if I have an indicator or an index that describe the quality, water quality status of my lake or my coastal system, I have to take into account a few aspects, basically 6 in creating an appropriate index that describe the goodness of your water quality in your coastal area or in your aquatic system. First, the timely detection of this. Can you use this index to provide near real-time detection? Is this index sensitive to pollution or water quality parameters? Is it sensitive also to the onset and the severity of this pollution even? There is another aspect which is a little bit more difficult after this pollution even happens, or bad water quality, for instance, even happen. Does this index also reflect what has been, what kind of damage has been inflicted on the field itself? So if you have aqua farms in your coastal system and you have an index of eutrophication, does this index, if it is severe or above certain threshold, does it actually indicate that I will have so much economical loss? And the fourth and most important part is that index should be consistent. How consistent is this index? When I calculate this index on a time series, does it actually relate to the amount of the water quality variable that I'm trying to describe? In addition to its temporal spatial representativeness, as you have seen in previous slides, we saw few fronts of, for instance, turbidity. So suppose this turbidity index also reflect these fronts. And last one, which is extremely important in our case, but also for the operational monitoring, how easy to calculate this index. There are indices, some of you maybe know, related to, for instance, precipitation indices, need probability distribution, fitting, and all other kind of extra pre-processing to reach these indices. So how easy to calculate that sometimes it helps putting that index as an operational to produce operational products from satellite. So how we derive water quality indicators or pollution indicators from satellite images? Basically, there are 3 families. Today, we will look only at the empirical algorithms, but there is something we call it semi-empirical and algebraic, and there is a fully analytical inversion. The empirical algorithm is basically you take what the satellite has observed, and you have some kind of, or some sets of in situ measurements, and you try to find the relation between satellite observation and in situ measurements. You can improve that, which we will do today, by taking a step further. Okay, I'm not going to look at individual bands of the satellite or the image. What I'm going to do is look at the spectral indices and try to create an empirical relationship with my in situ measurements. For instance, suppose you measure turbidity and you can create a turbidity index and relate it to the concentration of suspended sediment in your in your area, study area. There is another part which is algebraic, semi-empirical. This is mostly depending on fitting. So you have the satellite image or the satellite pixel. It has, we call it spectrum. A spectrum are the reflectance value per bands, per band registered by the sensor itself. We call this a spectrum. You take this spectrum and you fit it to an analytical or semi-analytical model that produce the water quality variables, and so you optimize till you get the best fit. Analytical inversion method, they are also similar to semi-empirical, but they have less coefficient that needs calibration. In our case, and today, we will focus on these empirical algorithm, and we will not use statistical inference, but what we will use spectral indices as a direct indicator of turbidity and eutrophication, how much algae or phytoplankton is in my system. And this is the whole part of the spectral indices. Normally, index, if you think about an index, in most of the time referring to spectral indices. When I mention spectral index, most of the time they refer to a sort of ratio, and they have a physical foundation based on how light interact with this specific water quality parameters. Most of these indices, they follow this simple form, which basically came from land application. Most of you have heard with this NDVI, which is normalized difference vegetation index, which takes the difference between two bands and divided by their sum. And this is the same thing, but the whole idea is to choose these bands in a very physical way, and we will. If you choose these bands in a very good way, then they could relate to some of these biophysical variables represented by your water quality parameters that you are interested in. You can go a step further and convert this index to concentration if you have field measurements. You can build up a regression analysis. For instance, this relation shown here is kind of a power law relation. It could be linear, it could be quadratic, it could be anything. It's just a statistical inference whereby you as a user could derive this model coefficients. In this case is the alpha and beta from regression analysis between your measured concentration and your observed satellite observed index. This algorithm and this family of application related to water quality detection from satellite are really simple, easy to derive. Even if you have limited measurements, they are very simple and easy to implement and get it on an operational phase. And here I three known water quality indices. They normalize different water quality index. This is a very important index to detect surface water bodies. This is for you when you have a small water body inland and you would like to delineate it, or you would like to study how this surface water changed with time, because surface pond or estuary, they are not fixed. You have a dry period, you have wet period, you have a small or region of water, or you have a large region of water. We will not use this one today. We will calculate it, but we will not use it. Just for your information. What we will use today and implement for the normalized difference turbidity index. and a normalized difference chlorophyll index. You have other indices like the algae bloom detection index. This is a little bit more complicated. It's not it doesn't simply follow the form of a difference between two bands. It has a more complicated form, but just I brought it to show you how you could calculate other indices and then do other application. They are more suited for other application. This index is really sensitive to algae bloom. So in your case, if your coastal system doesn't have an algae bloom, maybe you could better go with the normalized difference chlorophyll index, or you can apply them both. Now, for our case, we will apply these indices to Sentinel-2 MSI. Sentinel-2 is part of the Copernicus mission, and it has 13 bands. The number goes to 12, but just take a note that band 8 is repeated. You have band 8 and band 8A. These bands, they have a center wavelength. So if you look at the blue, for instance, is around 490 nanometer. They are here expressed in micron, so it's a 0.49 micron. The most important observation that the center of that these bands have different spatial resolution. So if you take band 1, which is at 0.44, which is 443 nanometer, it has a 60-meter resolution. The second band, which is also in the blue part of the spectrum, is about 490 nanometer, has a 10 resolution band, 10 resolution, spatial resolution. So if you want to build an index that combine two bands with different spatial resolution, then you have to do kind of resampling. You resample either to 60, either to 10, and there are also other red edge, vegetation red edge, band number 5 at 705 nanometer, which has a 20-meter resolution. So there are 3 different resolution of Sentinel depending on the bands you are using. So when you combine bands in either spectral fitting, in analytical algorithm inversion, or in empirical spectral indices, you have to take care and take notion that these bands, they might be or might need resampling to be to comply with each other with respect to the spatial resolution. So here in a normalized difference chlorophyll index, I will give an example of this index, and then I will go further to the exercise. It actually measure chlorophyll, and chlorophyll is the chlorophyll A specifically is the green pigment in an algae or in phytoplankton, if you look at a coastal system. And this is responsible for harvesting light using carbon dioxide and building the biomass. So this is responsible for primary productivity. The whole idea of this index is to use information from a reflectance peak. And here I show you reflectance from loaded with chlorophyll A with phytoplankton that has chlorophyll A pigment. And you could see that you have a peak here which is near 700. It's a little bit less than 700, but Sentinel-2 has this red edge band at 750, and this 705 is the center of the band. So the band is wider than this. It takes this peak into consideration. So the whole idea of this index is to use the peak in the red edge and the dip, which is caused by the absorption of this green pigment, chlorophyll A, at 665, and then try to build an index. As you see here, this is a spectrum of a water loaded with a chlorophyll. As you see here, in this case, the red edge band is higher than the red band. So if you subtract them, you will have a positive number, and this will give you indication of excessive amount of phytoplankton. Now, if the number is negative, that means the value, the reflectance value at 665 would be larger than the value at longer wavelengths, which indicates that the water is free of chlorophyll A. So they use this concept and they build a very simple ratio, what they call it NDCI. So it's the spectral index for chlorophyll, which takes the red edge band, band number 5, centered at 0.05, and then subtract from it the red band. And if it is positive, then I have a lot of chlorophyll in this case, and divide by their sum. So you get a ratio that vary between -1, theoretically vary between -1 to +1. And the negative values indicate relatively oleographic type of water. That means water with little phytoplankton, while positive value reaching the value of 1, it indicates eutrophic condition, water loaded with phytoplankton. You have to note that, as we mentioned, that band 4 and band 5, they are not at the same spatial resolution. So basically, you need to think about doing some resampling. So I use these indices, and these indices, they are related to some of those what we call them optically active constituents, those constituents in the water suspended and dissolved that affect the light field due to processes like scattering and absorption. And this is a very nice photo. It shows you a kind of eutrophication, even or bloom, algae bloom, I think in a Lake Erie, in between a state and Canada. But so if I have an index, chlorophyll index, I could use it to refer to the severity of this event, which is the departure from normal condition. I could use it to look at the timing, and also I could use it to look at the impact. And the impact here is a very complex term, because if I have a low severity, but it happens during a sensitive period of, for instance, spawning, it could have a higher impact than an event with a high severity that occurs outside of this period. So this is the impact here is not really a linear relationship with severity, is related to the severity, but also is related to the timing and to the location. So it's actually local or regionally limited or defined. So how we can go from an index like the normalized difference chlorophyll index to something that could describe the severity, the timing, and the impact of, for instance, algae bloom. We have to work with time series and anomalies. And this is very important. I will show you a few examples how easy it becomes when you take those spectral indices and you process them further into anomalies and monthly climatology. So suppose I have here, in this case, Sentinel-2. I have a few years of observation, and I take a monthly, I convert these data to monthly mean, and then I have in 1 year I have 12 months. So you can do all kind of calculation. The total amount of images you have will be, if you take the monthly average, will be the amount of months multiplied by the number of years of observation. This is the metrics we could see. What you can do all kind of aggregation. You can take a row, which is a year, and take the mean of it, so you obtain a yearly mean. But if you can take the column here, as you see, which are the months, and take the mean for each column, you get something we call it monthly climatology. That means the mean value of a certain month over all the years of observation. Monthly climatology is a really very important term because it allows you to look at the seasonal variability of your water quality. So it gives you an idea when the water quality conditions are at their best state or at their lower state, and this is seasonally dependent. But once you do this analysis or this aggregation on time, you could do something, we call it an anomalies. And anomalies is basically the value subtracted the mean. And the mean could be either the yearly mean, so you will have an yearly anomalies, or the overall mean, so the mean value over period of observation, which allows you to have a unanimous or not unanimous a reference to compare your observation regarding the overall mean. But if you subtract this overall mean, which is the mean which gives you the background of the water quality status in this system, you will get something we call them anomalies or standardized anomalies. Standardized if you divide them by the standard deviation as well. So you take the variability of that observation into account. You will get something similar to this curve. Suppose that you have a normal distribution. When you subtract the mean, every value that is above the mean indicate extremely turbid. And when you do a standardized anomaly, it has really a very nice feature. The mean of the standardized anomaly is always 0. And the standard deviation of standardized anomaly is always 1. And if you remember, it's plus minus standardized, plus minus standard deviation give you about 68% of the data are between plus minus standard deviation. But because you converted the spectral indices to standardized anomalies, now plus minus 1, because standardized anomaly has, they have a standard deviation of value 1. So it makes it very easy. You do not have to set a threshold from, it's just an arbitrary threshold. The threshold here is plus minus. a standard deviation. You could say plus minus half standard deviation, but then we come back to the arbitrary nature of that. But plus minus one standard deviation in a normally distributed data set, you capture 68% of the data. So if you have a very extremely clear water, you sit below 2 standard deviation, below the mean. But if you have an extremely turbid data, you would be 2 standard deviation above the mean. And this makes standardized anomalies a very suitable way to, as an index, to actually reflect the fluctuation of the water quality status. You can even very easily detect the onset of pollution even that affect the water quality, the timing, the duration, also estimate the severity. And I'll give some example. You will see it. So this is an example on 2 lakes, for instance. And this is an NDCI. You could see this lake on the left side has some clear area in the northern part, while the other lake on the left, on the right-hand side, on average, this is an average over 7 years of Sentinel observation. You could see is on general a little bit more turbid. So from this NDCI calculation, I go ahead and I calculate the standardized, and I convert here the standardized anomaly a little bit. I just flip the sign. So everything above the 0 is good water. So it's oleogotrophic. Everything below this is below 0 is eutrophic. And then you could define a region where you consider it a normal. Here I just put it as a 0.5, so quarter of the standard deviation. And you could see immediately, for instance, if I look at the first lake on the left-hand side, you could see immediately that I have here in 2022 to 2020, almost 24, before 23, I have a big event where I have kind of eutrophic conditions. It was broken with a event. So you could immediately detect the onset. We could zoom in and define the month where it started. You could indicate the duration, but also the severity. And on the severity, you could think about measuring the area, this shaded area, for instance, which combine the duration and the intensity. You do that for each lake and it gives you immediate, and then after that you can build a small algorithm to detect when these values are above or below 0 and how long it took it to come back to the normal condition. And so with these anomalies, it gives you basically a tool to identify when and where you have pollution events or alarm for the water quality status in your area. One of the application of this anomalies, for example, I give you here is the same 2 lakes. I switched them, but the same 2 lakes, I use the anomalies, and then I count how much times the water was clear, and I just put here the count. So this is the frequency in months. I have 7 years, so you can estimate 7 multiplied by 12 because I convert them to monthly mean. Then that is 84 images. Because of the area, there are images, there are months that has no images due to cloud, so you remove them there and you will get a little bit less than that. So this is the lake where we have seen in the beginning that it is in general has more eutrophication. The overall average has shown that you could now count how many times the water was clear with respect to total or overall average, and you could identify area in this lake that basically the water condition are in most cases good, but the rest of the lake is not actually is not good. It's mostly eutrophied. But if you look at the other one, which is for instance, this region has on 7 years average has in most of the time the best water quality. And this is a very nice tools. You use a very simple index to detect and to count the number of months where a specific area has exhibit I just come back to these two lakes. You could see this lake, for instance, where clear water is expected to be here, and you could see it back indeed has been detected, but then we can put number of it. So 55, the highest number is I think 60. So only in the middle, I have 60 months where the water condition shows acceptable above the mean, where here you could reach to more than 74, I think, but you could see it also from the view of the figure that if I wanted to make a swimming advice, give a swimming advice, or I would like to tap water from this lake, then the upper right panel is a more appropriate lake than the lower left to tap water. And from the upper right panel, actually the north eastern side of the lake. So this side is a more appropriate to tap water, for instance, or advice for swimming. So what we have seen today, we have seen that atmospheric correction extremely important for above water. I show example on only 800 meters. So can you imagine if it is totally out of the atmosphere at 800 kilometer? So atmospheric correction is really of prime importance, importance to water quality application. Indices in most cases are computed from indicator, but normally we refer to two, more than one band at least. But they both compress the information. As you see, you put two bands in one index and you say this is more related to chlorophyll, for instance, or to eutrophication based on physics. There are three approaches to derive water quality indicator. Actually, these are the approaches. Either you use empirical approach, semi-empirical, or fully analytical. There are many techniques to apply these approaches, like lookup table and optimization, using spectral fitting and so on. But only three main family to derive water quality indicators. When you have a pollution, even you can actually characterize this pollution even using anomalies, because it gives you an indication of the severity, departure from the mean, the timing, and also you can calculate the impact if you wish. And this is better assessed with time series. Now we have finished the theoretical part. I would like to show you an exercise on big data and cloud computing, but I would like first to receive a question. You can pose your question in the question and answer box, which is, if you see it on your screen, it's between the chat and the people. There you have a question Q&A. So if you have a question, please pause. We will go further with this idea of so what you can do, what we have said, actually you can apply it exactly if you go to dataspace.copernicus.eu. This is the data space ecosystem of the Copernicus program. It provides you with tools, but also cloud computing capability and storage to put your data and test your data. So I will just you may not know it if you are not registered. You need to register to create a free account. It will take about a minute. They are very fast and efficient, so it will take about a minute to get actually access to it with a password and an account. So try to register, and I show you here the arrow to register to this data space Copernicus. So I will give you some times to look at it, but then I will check the question and answer session to see if Alex has posed any question. So when you register to this, or if you have already account, just go to dataspace.copernicus.eu. You will get a panel with analysis data. You could choose Jupyter Lab, and from there you will get this Jupyter Lab, and you can access this Jupyter Lab. I will do these steps right now. When you access this Jupyter Lab, you will get actually an account, so you can register in. And I will switch to the website. So I will share this Jupyter notebook with you later on, but let me show you. This is a very nice example that applies all the steps we have seen in the lecture. Applies all the steps that we have seen in lectures to come up with a very nice index, chlorophyll index, but also turbidity index. And we convert that to anomalies, standardized anomalies, and we could see really very nice patterns. So we will also learn about how to carry masking, because you see an image water and land. You do not want to process land pixels, so you do water masking, and based on a spatial or based on a shapefile. And today we will focus on these two indices, one for turbidity and the other for chlorophyll, and look at how you visualize the results. So we hope that at the end of this exercise, you will be able to or have an idea how to use satellite data, access these indices or calculate them. This exercise is partially based on basics that's also available from this Copernicus dataset and Copernicus ecosystem. I will just go back and show you how it looks like. So you have actually to go to the data space ecosystem. You have to log in here, which I'm logged in, and then you go to analyze data and you go to Jupyter Lab, and then you can access this Jupyter Lab. And here you will have samples, you have my storage, but you will also have access to these samples. So I will click at these samples. You have many samples here, different approaches and testing different tools. I will be using that. I will just go to my storage, and here I have a small workflow that implement a few steps to reach to an index that could give me an idea about the severity and the timing of a pollution event. So first of all, we have to import fuel library. I do this process just to give you an idea that if you have here storage in this data space ecosystem of Copernicus, I think you have to be active. Otherwise, it will be deleted after, I think, a week or two. But also the packages that you have installed, it will be removed. If you hear me, can you raise your hand? Thank you, Alex. Thank you. Okay, so you hear me. Brilliant. Again, I'm still waiting. Apart, I have your question. Apart from chlorophyll A, turbidity, and TDS, there are some water quality parameters that we can derive from Sentinel-2 images? Yes, I will apply. Yes, you can derive dissolved organic matter. So basically what you can derive is only those constituents that they affect the light. Either they scatter, either they absorb. So you can derive chlorophyll, derive suspended particulate matter, and you can derive dissolved organic matter because they have only that part that absorb the light. You can derive it. But you can derive, these are the direct derivation. You can derive indirect indicator like the nitrate and nitrate because they are somehow related to the biology, so they are somehow related to chlorophyll A. These are indirect, so nutrient, you can derive them indirectly. And there are some models, for instance, to derive the dissolved oxygen, but these are indirect models. So they are empirical in nature, or they use biological relate some observed variables like the temperature or the chlorophyll A, relate them with in a small or simple or maybe more complex biological model that leads to detecting of dissolved oxygen and a nutrient. So there are direct and indirect. The direct retrieved products for water quality from Sentinel-2 on any other sensors that has this band setup are basically chlorophyll A, total suspended sediment or matter, and suspended particulate matter, and dissolved organic matter. Any other variables are indirect derivation and could be either through empirical statistical technique or biological, biophysical models. So these my answer to the question. Thank you, Alex. So I will go and then share again. Again, so this is the exercise. I warned you that when you open my storage, you have to download everything you do there to your local, because these data or my storage is being emptied each, I think, 2 weeks. I do not recall either 2 weeks or either 1 week. But also the packages. So if I use here a Python kernel, you can use other kernel. You can select other kernel depending on the depending on your application, either geoscience or OpenEO, Sentinel Hub. I just use the Python, but this also requires that you have For me, I have more control on what I do. So you can install, you have to install these packages that you need them. So you need different packages that can deal with the satellite data and manipulate them. So I install these packages here. And then you have to connect to the OpenEO data space Copernicus to be able to access the data. Um, and after that, you have to authenticate. This is basically will ask you to log in. And then after that, what you do, you define the west, south, east, and north. These are the box that define your study area. You put them, and then you ask the OpenEU to extract this area for you. Of course, you can define a time series from, this is, for instance, example of 5 years of observation from Sentinel 2. And if you look carefully at these latitude and longitude, they are basically around Mombasa in Kenya. You could think about resampling. I would like to see my map them in WGS, for instance, so plot them in lat long, which is really nice, but it has a disadvantage, and you will see that that if you would like to sample to, for instance, 10 meter, which is the highest resolution Sentinel-2 has, then you have to choose this 0.0001 degree. But you can, it's better to do that in a UTM projection system where you can define the resolution in meter and put it simply 10 meter. But here I give you an example when you do that. On how it translate this 1 per 10,000 degrees on longitude or on latitude. It's about 11 meters, so it's about the 10-meter resolution. Again, you can do that in UTM zone, UTM projection, and you can say, okay, put it instead of this resolution in degree, where you see it here, you see you can put it in meter. But I did it that way because I would like to visualize later. You will see with lat long. One of the things that you have now took the data and you need to either visualize them or download them. I would advise you to download them first, because this will make it much easier. This step will take the most time. So you download the data, and then you can ask them again, read them as an X-array. When you read them as an X-array, now you can visualize them. Now you can do calculation with them. You can also do the calculation and visualization on this data before downloading, but you have to do it with the command, we call it execute. And that execute, it takes the data from the server to you. But this will take as much time as download, but with one disadvantage, that if something happened, then you will lose all your work. So it's better to each step take a moment, download your data to your my storage, and do not forget your storage will be deleted after a while. So after you finish the session, it would be good to have it on your local disk. So I will download the data. Now I will read it now because I did this step, so I'm not going to do this step, but I will run the step where after downloading the data, I read it to as an X-array. I will run it this one. See, it runs very perfectly. And I will count how many number of images I have. So I take the coordinate of time and take the length and the number of images. I have 55 images that satisfy the condition. Look at this condition. It's between 2020 and 2024, and it has these condition maximum cloud cover. So I have more images, by the way, but these, they could have exceeded the cloud cover that I put. So in theory, it is better to have a little bit relaxed threshold depending on your area. So in this area, you have a lot of cloud cover, as you could see. Visualization of the area. I think this is in Kenya, it's in Mombasa, but I will come to that later. So now you would like to visualize it. So you visualize the band 4, 3, and 2. And if you remember, I can show you the slide again, but band 2 is basically the blue band. Band 3 is the green, and 4 is the red. So basically you are visualizing blue, green, red. So it's kind of a true color composite. So you put the data put the band in this data set, and then you visualize them. What I do here is I visualize the first time period and last time period, and then you would see how it visualizes. It will take a little bit time, and okay, it comes here. So the first time period of my 55 images is 21st of January 2020, and the last is 20 of December 24. And you could see in both images there are many clouds, but because I did the projection in WGS, it's easy now to have a latitude and longitude. So for the people that actually are in that area, or they know the area, they could relate to these latitude and longitude. You could do it with UTM. It makes it easier to choose here approximately 11 meter. But when you plot it, you will have here X and Y in meter, which is a little bit confusing. But you can do both. You can first use UTM, define the resolution, and then use WGS 84 to visualize. But it is very easy to do both. Now, as you have seen in this area, I have a lot of cloud. I have a wet and dry season, and during the wet season, yes, it's wet. So it is raining. And here is the thing. Optical images, they suffer from cloud cover. And as you see, when you have cloud, actually you have no data. You just have no data. And from 2020 to 2024, we have selected only those images that they have in total less than 25% of cloud, and we got only 55, which is pretty low, by the way, because you have to consider that I have each 3 to 5 days one image, because I have two Sentinel-2A and Sentinel-2B. I'll just take an average about 5 days, and then you will have in a year 360. So you multiply, just to have an average. So you will have about 75 images a year, and it is 5 year. You multiply it by 5, so you should basically have about 300 to 400 images on that period. But yet, because when we inquire on those images, we need less than 25% from those 400 images, or we have about only 55, which is 12 to 15% of those images. And this is one of the not limitation, but this is one of the, yes, limitation of optical observation that we have to deal with it. So as you see, if there are cloud, I see nothing. I have here, for instance, cloud, I see nothing. And in addition to that, to make life a little bit more complex, if I have cloud, I will have a cloud shadow. So also the shadow should be removed. If you see this, for instance, cloud, you have a shadow. So the sun is coming from that direction to cause this shadow, and this shadow should also be removed. There are different ways to remove a cloud, but we will not make investigate in that because this is not the essence of the course. You could use this band, which is the provided by Sentinel-2. It's a classification map, classification band. It has the 10 values that describe each pixel. Is it a saturated defective, or is it bare soil, vegetation? Does it has a cloud with high probability of cloud with low probability? Is it a thin clouds, or is it the water? So what we will do here, we will just implement the thing, because I would like to show you something here very important. This area has also some heavy vegetation, and it has some water outside of the main water body. So when you apply this, you could take this as a SCL band, and you tell him, oh, I would like to mask all value that are not, where is it? Sorry for that. That are not water. So the value of water is 6. So I will mask all value that are not water. I will be masking them, and you could choose this mask. You have also to watch out that this mask should be also resampled to your original sampling. So if you choose, for instance, 60 meter, then you have to resample to 60. If you choose 10, you have to resample to 10. But what very easy, you take the cube that you have resampled here, and you resample the mask to it, regardless. You don't have to repeat the same thing. After you do that, it's advisable again to download. I do download here, and so do that, because if you do not download and you lose your work, and you have to repeat everything again. So I download here. So it's always good to download each step, and then be mindful when you repeat the processing that you do not have to download it again, or you have just to be mindful, because when you download, you actually are certain that the work and the processing will not be lost due to some problem, server shut down, or you have problem, or you did a mistake. So it is very nice to download these data, and as you see, they are downloaded here in my storage. That each time you do that, do it in an organized way, and take your data from data space, the Copernicus data space ecosystem, to your local, because you have a limited amount of data storage, and it can be filled very easily. I think it's 10 megabyte, and they cannot keep it for you always. So you have to clean up your products. Now I download it, I can open it here and visualize it, and I will do that. And you see it's running, and here is the thing. So I removed the water. I took a true color image. Again, band 2, 3, 4. Band 2 is the blue, band 3 is the green, and band 4 is the red, and I visualize it. And here is the thing, you see that the water mask is not really good. And this is very important for us to notice. So basically we have to, if we wanted to calculate, or we wanted to mask the water, excuse me, water, we have to do additional processing. If you apply the same approach on a different region, you might get a better masking. So be aware of that this masking of water pixel is not enough. But it's for me to show you these small, delicate observation, and I will show you a way to improve on that. Now we would like to generate those water indices, you remember? And these are the bands of Sentinel-2. I put them here to remember and to remind me that actually these bands, they have a different central wavelength, so they bring different information, and ESA has provided us with a kind of semantic to understand what kind of observations. So for instance, band 1 is better to detect coastal aerosol. Band 9 is focused on the water vapor absorption, which is at 945 nanometer. And also to remind me that those bands are at different spatial resolution. If you remember, I have done a nice task here already. I thought, I will take this Sentinel, if you remember this task, I will take this Sentinel cube and I project it all to 11 meters. So I have all my products. Now all my bands are on 10 meter or 11, to be precise, 11.1 meter spatial resolution. So I do not have to worry about it. Now, these are the normalized water index, the one that I mentioned, but this is based on the same concept, the difference of two bands divided by their sum to delineate water bodies. So I can, in principle, use the information in this index to improve my water mask. You remember, I use the water mask that is supplied by the sensor, by the product of the Sentinel-2, but this, depending on the area, we have to be careful. We have to complement that with this NWI that calculate the water, or it gives you an idea about the water existing water bodies in a scene of an image. Positive value are most likely water, negative value are most likely not water. So you can calculate the index and say everything, remove everything below equal or below 0, and then you will remove the land. So you could clean up these areas here. We have the normalized difference turbidity is the same concept, the red minus the green divided by their sum, but the normalized, let us focus here on the normalized difference chlorophyll index, which I have explained in the lecture. Again, the same concept, but a slightly bit different physical interpretation, and the whole physical interpretation is based on a clever selection of the bands. And here we select, for instance, the band centered at 705 minus the red band centered at 665, and by their sum. Now I just assign those to new variables. I call it the green band, red edge band, and I just calculated the normalized difference water index, but then I calculate the chlorophyll A index, which is the normalized difference chlorophyll index, and the turbidity index. And again, do not forget, download the results. And I have download the results. Just to, I calculate the mean over the whole period, the mean and the standard deviation. You need them later on to calculate the anomaly, which is very easy. You just reduce dimension and you tell him what kind of dimension you wanted to reduce, which is the temporal dimension, and you take the mean. And you can download them. You can do the same thing, reduce dimension, and you tell him reduce it as standard deviation, and you download this. You need this data later to calculate the standardized anomalies. So now I load them again, mean a standard deviation, and I calculate the standardized anomaly. Here's the thing. A standardized anomaly is explained here, is basically the value within 1 month or within 1 day, or the observation, minus the overall mean. And if you would like to calculate the standardized anomaly, which is here, divided by the standard deviation over the whole period. The nice things, as I mentioned during the first part of this webinar, that this gives you a distribution that has always a zero mean and unity standard deviation. And as we know, if it is normally distributed, plus minus 1 standard deviation is the around the mean value, and which is 0, and everything above 1 or below 1 actually define immediately extreme events. And this is really the nice things about it. So I calculate this anomalies. And here it's very simple. If you load it as an X array, you just do a calculation in X array as shown here in the equation, which is the value within 1 month minus the mean divided by the standard deviation. And I plot the figure and the mean turbidity. Again, as you see, I did not improve the land mask or water mask. We should have improved it, but let me go further here if you do not mind. I need to calculate those. I did not. Oh, sorry, I need to calculate those. It will take some time because I'm loading these data. See, it calculated, and now I can plot the overall mean. It will take a little bit of time, but then it will plot it. Again, we did not really improve on water land mask. We should have, improve it. And then calculating the standardized anomalies. Now I'm trying to calculate one time series. And here's the thing, you have to watch out, like some months in that area could be over the 4 years very clouded, and I do small calculation and I found that actually month number 7, which is July, in these 5 years of observation, I did not get any image that is below 25% of cloud. That is a very good indication that I have to relax my cloud percentage. You see here, you could see it here. I did some calculation here, and I told him, show me the missing month. And he told me missing months is 7. I have January, February, March, April, May, June, August. So he skipped July, which is month number 7, September, October, November, December. So if you would like to have some data on the month of July, you have to relax the percentage of your cloud. Excuse me. And hopefully you will have, maybe we don't, maybe this month is always cloudy. But these are the small tips that you, or the small details that you have to take care on that. Now, let us calculate this time series. What we have done, I told you that climatology are extremely important. So what I have done here, if you remember, we have a matrix, the year of observation as a rows, and actually the month of observation as column. And each aggregation level, each temporal aggregation level will serve a certain application. So if I aggregate on a month, I will get monthly climatology. So I will convert this 55 images to only 12, each one representing 1 month. Except for July, because I could not get data for July that satisfy the condition of lower than 25%. And I also calculate the standard deviation. And in this area, you could see, I plot that, you could see the seasonal variability of this chlorophyll index. So basically, I have 2 seasons where the chlorophyll index is exhibit low value, and I have also 3 almost seasons where or 3 periods where the chlorophyll actually exhibiting a high value, and this is for 5 years of observation. You can do the same thing to calculate the anomalies to get exactly the same thing, and then you can calculate the value of anomalies, how much months was above the mean and how much months was below the mean. But I hope that I have shown you with this small exercise. I go here a little bit and then I do some kind of calculation. I still have something here. I think this has to be T to show you how things works. Let me see. Where is the time? I still have time here. That is T. I tried to calculate this anomalies for the whole years and a little bit try to look at plus minus 1 standard deviation. You can relax this a little bit, for instance, to 0.25. So this is the same, sorry, the same as my figure. And you could see that in most cases, I have a good condition in this region. Basically, in 2020 till 2020 was a good year with a kind of oligotrophic condition. The condition have been a little bit worsened starting from 2022 to 2024 and 2024, and this is based on the chlorophyll anomalies. So let me just improve this figure, if you allow me, before we finalize our webinar. So now it is better suited in that way. So in most of the time it is normal conditions. Again, in 2022, starting from 2022, you could see that the condition has been more worsened. So there is a kind of sign of eutrophication or increased frequency and probability of eutrophication. Just look at 2022 here in that area, and then look at the left. You could see anything below or below zero, below zero or below, in this case we put the threshold 0.25, indicates a very good condition. And 2022, everything zero actually indicate less good condition, and you could clearly see the area from 2022 is or is witnessing an increased eutrophication. And you could play with this. Basically, the main average is the 0.1, so you could do that, and I will just give you the average of 0, so you could just and then maybe I did a small mistake, but this gives you a good idea. Let me just repeat that one. This gives you a good idea about how with the simple but thorough way of analysis, I could actually spot in an area, I've never been there. I could spot that in Mombasa Bay, starting from 2022, I have a more frequency of having eutrophication, so increased algae blooms in that area. And while in 2021, 2020, it was a better conditions. So I will stop here. I hope I could show you the utility of this cloud computing in a less than actually 30 minutes. What we have done, we have basically downloaded the almost 5 years, not almost, actually, we have downloaded the 5 years of observation from Sentinel-2. You can download the full archive, which it goes to 2020, 2017. You have download, but just now for the sake of calculation and the sake of this webinar, you had access the 5 years of Sentinel-2 observation. You have calculated a few indices. You have applied aggregation in time and space. And then for a certain area, you got it and you analyze July, for instance, has cloud above 25%, and that's why we missed it. You could calculate and visualize the mean. You discover that having this simple band classification of the water is not enough. So for this area, I need a better approach to classify water pixels. But you could visualize the mean value, which is really nicely shown here. You could look at the spatial pattern, but you could here look at the temporal pattern, seasonal pattern, and finally, you converted this spectral index to standardized anomalies, and you calculate the anomalies for the area, and you could identify that from 2022 till now, the situation has been more towards increasing probability of eutrophication. I will stop sharing and I will be happy to receive your question. Yes, Alex, please pose your question. I'm not sure if Job could give you the mic, but if it is not possible, then you can unmute and ask your question immediately if you can. Oh, now I hear you very well.
Yeah, thank you very much, Prof. My name is Alex Saturday. I'm a Ugandan. You
Nice
can't
to
hear
meet
me?
you.
Yeah.
I can hear you very well.
Yeah, sure. So my one simple question. I am someone interested much in the chlorophyll concentration, using those indices to assess the quality of water. But my simple question is, how much time do you think is adequate? I am someone who is not familiar with using the Sentinel images. I have for a very long time been using doing the laboratory analysis, picking samples, laboratory analyze. But then this one, I actually find it much more interesting. But my question is it something that one can give a try and get to know how to use it within, for example, 1 month, 2 months, days, so that I can start applying this? That's my question before you. Thanks.
Okay. Thank you very much. Basically, if you take the materials provided in this webinar and this Jupyter notebook that I've used to showcase, you just have to change these lat long to your lat long and run it, and you will have immediate. You have to wait a little bit and be careful in saving the data and so on. But within a day, you will have a first indication of the usability and the applicability of Sentinel-2 data to your situation. So it I would advise you to first try it. It will cost you a day or two, but it will give you immediate results. And then from your local data, you have to see if this index still need calibration, because this index is unitless. It's not in microgram per cubic meter like chlorophyll AR measured. I think you might be using a technique in the lab to look at it. It is an index, so you might need to, if you want it in concentration, you might to do a extra step, which you calibrate this index to your own measurements. But it will give you an immediate temporal and spatial pattern, and this is the strength of satellite observation. You have to be very careful of not comparing a value coming from a pixel to your measurements, because you go to the lake. I think in Uganda you have a few lakes. One of them is very famous, if I recall. You pick a sample, and this is a few liters. You filter it, and you filter, I think, 1 liter. If it's too eutrophied, you cannot even filter 1 liter. So you filter 1 liter, say, but a satellite pixel here, in this case, is 10 by 10. So it's 100 square meter. And suppose, just for the sake of comparison, you have a penetration depth of half a meter. So 100 multiplied by half, this is 50 cubic meter. So you are comparing a satellite pixel that sample 50 cubic meter in a conservative measure with half a liter. So this direct comparison is a little bit tricky, and it requires a lot of attention. But what the satellite gives you, and for sure very accurate, is the spatial distribution, the spatial pattern, and the temporal pattern. And that's one of the reasons that in my webinar, in our webinar here, we calculated the anomalies. And the anomalies, they remove the mean and normalize for the variability. So you have a kind of a standardized measure of the temporal, but you can also do it for the spatial variability within the satellite. And this is the technique. No other technique can give it to you. This is spatial coherency, spatial distribution, and temporal distribution. But now, be careful, you cannot compare magnitude to magnitude. You have to do it at a certain stage if you want to calibrate your model. But if you are at this stage, I can advise you, you have to follow a certain procedure to do this calibration. Did I answer your question, Alex?
Thank you very much, Prof. Yeah, you actually answered it right. But now my only worry is that there is some work I am trying to propose, and I wanted to look at an aspect of making a comparative analysis, because recently there are some perimeters that can be used to measure chlorophyll A while in the field. And then that is a bit, because the science in there is a bit different from if you pick the samples and then analyze them using the spectrophotometer. So what I actually wanted to do is to assess, the accuracy. But now you are telling me that is a bit difficult, because I wanted to look at data collected from Sentinel, and then vis-a-vis what is measured on the field, while in the field, and then the data collected in the lab using the spectrophotometer. So now in my little understanding of how Sentinel-2 works, I thought that is possible. Yes,
it is
I
possible.
think I now need to get back.
It is possible, but what I meant is not difficult, but you have to be careful. For instance, can give you when you would like to do calibration, and this is what you are opting for. So what you are opting for is to have this spectral index, compare it to your chlorophyll A measured, and then try to look at the regression, do some kind of regression analysis with them, right? Here you have to follow a certain procedure. For instance, first you have to choose the pixels of the satellite that coincide with space, lat long, and time with the measurement. So we call these match up, and it has two specific characterization. First, it has to be the same lat long. Second, it has to be within 2 hours of the satellite overpass. So I have to know the satellite overpass locally. So suppose I measure I measure this location at 10 o'clock in the morning, and the satellite overpass is at 9 o'clock in the morning. This is within the limit. But if I measure it at 2 o'clock in the afternoon and the satellite overpass is 9 in the morning, this is not a matchup. So a matchup is a pair of that consists of observed pixel from point through field measurements that they match in time within 2 hours of satellite overpass and in space. Now the space issue is a little bit also tricky because the satellite, you have to be careful because satellite pixels are grids. So suppose and when you extract the lat long of each pixel, suppose you extract the center of it. Now suppose you are measuring at the edge of that pixel in the field, which value you have to consider, the one closest to the center, that pixel within that pixel, or the other pixel. So what we do is we take the measurement point, the lat long, and we try to average to avoid that one. Average at least 3 by 3 pixels. This will avoid this discrepancy, but it has a limitation that the measurement point should be sufficiently far from the shore. So when you average the 3 by 3 pixels, you do not get the land. And I know from water authority, at least in the country that I work with, that they measure in jetties. They do not go with a boat to measure. So they put their instrument in jetties. And here's the trick. If you wanted to average 3 by 3 pixels or take the pixel that match the jetty, you might get a piece of land. So there is another approach to do that. And I can go on and on. And this is what I mean. You have to be careful when you compare value with field measured value, specifically for water quality issue. You have just to be careful. You have to follow the procedures. The procedures are published, by the way, and they are online. So the standard to do that, and this is what I mean. You have to be careful. Is difficult in the sense that there are many steps and many cautions that you have to take before having a final conclusion. Clear?
Yeah, thank you very much. Yeah, sorry for dominating the rest. Is there an opportunity that we can have this next time? Because for me, I'm attending this for the first time, the very first time. I don't know whether there is an opportunity in the near future.
Yes, we have a face-to-face training that will take place most likely in Alexandria in Egypt, and this will be in December, just before the Christmas break. And I think there will be kind of limited support for limited number of persons, but I do not know really the details, but I know that there will be a face-to-face training. This is one. A second one, we have these trainings also online through the EU Africa. You can access this Jupyter notebook through the online materials. You can access the lecture, also the same one I gave, also through the online materials. So if you have access to the EU for Africa portal, then all these materials are already presented in a Moodle format. So it's kind of online material, and they are there, the Jupyter notebook and the lectures.
Thanks.
You're welcome. Thank you very much for being active and asking question, Alex. Any other question from other participant? Okay, then if there is no other questions, I would like to thank you for listening to this part of this webinar. I hope it will help you in the future in using this type of tools and technology to address water-related risks, specifically pollution-related, water quality-related. And I hope to see some of you during the face-to-face in Alexandria. I think it will be 15 of December, if I'm not mistaken. But in that, just a week before Christmas, there will be kind of support. I think there will be limited seats to get the support, so you can travel and attend the meeting. This is a face-to-face training. But again, all these materials are available online through the EU Africa platform. Thank you very much. All the best. And if you have anything, you have my email, please send an email. Do not hesitate. Thank you very much. Bye-bye.